Here's a quick update on the performance issue. The experimental I2C implementation works in principle, but is way too slow for bit banging over GPIO without throwing a screaming tantrum. Luckily, the IO-Warrior40, and I'm aware I'm starting to sound like a salesman for the company, offers a solution which isn't lightning speed, but will be enough to send simple commands back and forth. The specification promises 750 bytes per second, so let's see. The communication between device and computer is based on USB. Since USB is a message-based protocol, the API's implementation is also message-oriented, or as the manufacturer calls it, reports. I'm guessing that's technical USB lingo. For now, I'll use the terms message and report synonymously. The reports are used for everything, to control GPIO status, device settings, I2C inbound and outbound messages. It's all the same. In any case, the messaging frequency is limited to around 125 Hz. By putting more data into a single message and letting the device handle the data and clock lines, the bandwidth can be increased from 1 byte per second to 750. The API header defines a bunch of report types for different devices and purposes. The one dedicated to I2C is IOW-Kit Special Report. The structure has two members, bytes and report ID. The first byte of the array usually holds information about the message itself. The report ID determines its purpose. The first message you're going to have to send is the initialization report. The report ID for that and shutdown as well is 1. The least significant bit of byte 0 starts or stops the I2C mode. When I2C is enabled, pins 6 and 7 on port 0 can be used as clock and data lines. Byte index 2 is an integer multiplied by 500 microseconds, representing the time the device will wait for the slave to respond or something like that. But honestly, it doesn't do much for me, so I just set it to 16 milliseconds, which should be twice the average round-trip time for a message and response. No well. So this covers the start and stop of the I2C mode. Next thing is the write message using report ID 2. Byte 0 carries a bunch of flags that define the structure of the message. To write a single byte, you need the start and stop conditions and 3 bytes of data, which will be placed at positions 1, 2, and 3. Keep in mind that everything you see here is handcrafted for the communication with the X24C16 chip. Once the message is sent, and here's the tricky part, the device generates a response report which must be fetched using one of the read functions. The message will have report ID 2 as well and will carry a 3-digit integer in the least significant bits of byte 0, representing the number of successful acknowledge bits. The write message has 3 bytes, excluding the flags, so you can expect 3 acknowledge bits in return. Besides the regular write function, you're also going to need a dummy write to set the EEPROM's memory pointer. As you can see, it's almost identical, except that it's missing the payload byte and the stop condition. If successful, the dummy write will return 2 acknowledgements. The read function that I have here is actually a sequential read. Byte 0 specifies how many bytes are expected from the device, with a maximum of 255. Byte index 1 is what the specification calls command byte. In the case of the X24C16 EEPROM, it's just the regular device and bank address and read flag combination. Once sent, you gotta keep calling the read function again. This time the response is going to be report ID 3, and depending on the number of bytes requested from the EEPROM, you're going to get multiple reports in chunks of 6 payload bytes. This, by the way, explains the maximum bandwidth of 750 bytes per second. 6 bytes per message at 125 Hz. Okay, so let's give it a little speed test. I've got my user interface here. You might remember it from the last time. This time with a couple of new buttons. So we got the clear button that simply clears the canvas with some random noise. Then there is 2 write functions. One is going to write a checkerboard pattern, and the other one is going to write a random noise. Next to that is the stop button, which is going to stop whatever transaction is currently going on, and a read button, which is going to start the whole reading sequence. Technically, it's going to start with a dummy write that will position the internal memory pointer to position 0, and then it's going to go with sequential reads of 32 bytes per call. So I got an EEPROM plugged in, and I'm going to start with writing a random pattern. And by doing that, we can hopefully find out what the writing speed is. So now that it's done, we can take a look at the console, and that tells me that the whole procedure took 16 seconds, around 16 seconds. So if we take our 2048 bytes, divide that by 16 point something, so that gives us around 125 bytes per second. Now, how is that? Internally, I only used 1 byte of the 6-byte message. So I could have sent 6 bytes, but I only sent 1 byte. So if we multiply that by 6, and that gives us the promised 750 bytes. So now that the random noise is written, I can start another writing procedure, this time with a checkerboard pattern. This is just for my personal amusement. And I'm going to let that go until roughly the 4th button. Okay, so I'm going to stop that here. On top of that, I'm going to write another random pattern up to the 3rd button. I'm going to stop that. Now another checkerboard pattern. I'm going to stop that here. And finally, some more random data. Okay, so now I can clear the canvas and read the whole thing. And that went a lot faster. Like I said, it reads 32 bytes per call. So if we look at the console, the whole thing took like 3.5 or something seconds. And that makes sense because with the writing, I had to call the write function 2048 times. And with the read function, I only had to call it 256 times, so just the horizontal axis. So yeah, there it is.